Intelligent Transportation Systems Podcast. Welcome to the ITSPodcast. This is episode 24 December 2014. I'm Javier Sanchez Medina from the Intelligent Transportation Systems Society. This is our Christmas present for all our appreciated listeners. We have prepared a very interesting episode, including a super instructive long interview with Professor Azim Eskandarian about active safety. I'm sure you'll like it. Additionally, we also have a transportation in history mini-section by Mehran Shirazi as usual, this time about manned electric aircrafts. Really refreshing. So that's the plan. Please get comfortable and relax. We'll start now.
Transportation in History by Mehran Shirazi, PhD candidate at Simon Fraser University, Canada. Have you ever thought while sitting in an aircraft during taking off, something like, well, an electric engine couldn't do this? Did you know there has been manned electric aircraft since the 70s? Actually, electric flight goes back surprisingly far. In 1884, there was an electric-powered French army airship called La France. The 52-meter-long airship covered 8 kilometers in 23 minutes with the aid of a 6.3 kilowatt electric motor. It could do what no balloon had done before that, return to its launch location at the end of the flight. However, after this early success, all went silent on electric aircraft for about 90 years. The Renaissance began in the early 70s, when electric models were used in airplanes and a couple of pilotless solar-powered aircraft was built. Militsky MBE-1, the first aircraft carrying a human passenger and using just electric power, flew in 1973. Its creators, Fered Militsky and Heino Berdichka, converted a Berdichka HP-3 motor glider into an electric aircraft. The first manned flight was performed by Heino and lasted for 14 minutes. In 1979, the Mauro Solar Riser was the first electric manned aircraft to fly on solar power. It was created by Larry Mauro, president of the American Ultralight Flying Machines Company. The first man-carrying flight was performed in April 1979 at Flabob Airport in Riverside, California. The aircraft reached a maximum height of about 12 meters and flew 800 meters. Mauro Solar Riser had modest results regarding autonomy, but paved the way for more and more similar projects. The balance between the energy spent by electric motors and the energy that can be accumulated from the sun is the central equation of such projects, aiming at a virtually infinite autonomy. That is exactly the plan of the Swiss-based solar-powered aircraft Solar Impulse. This crowdsourced, super exciting project has ambitions to perform a non-stop flight around the globe in 2015. Electrically powered aviation projects are fun indeed. You can easily imagine engineers having a great time with them. For example, there was that project developed at Tokyo Institute of Technology in 2006. They developed a manned prototype powered just by commercial AA batteries that flew for 59 seconds and traveled 391 meters.
Hello again. It's now time to start with the main course of this episode, our interview with Professor Eskandarian from George Washington University. It's really interesting, you will enjoy it. Hello, we're today with Professor Azim Eskandarian. Professor Eskandarian has a long experience in dynamic systems, control and intelligent systems, and applied and computational mechanics, in particular applied to automotive engineering, transportation safety, intelligent vehicles, and robotics. He is director of the Center for Intelligent Systems Research at George Washington University in Washington, D.C., USA. Among the vast experience fields of Professor Eskandarian, we want to talk to him this time about active safety. Hello, Professor. Can you please introduce yourself to our audience?
Yes. Hello. My name is Azim Eskandarian. I am a professor at the George Washington University, where I've been for the past 22 years, and I also direct a center called Center for Intelligent Systems Research. And prior to GW, I've been working as an assistant professor at the Penn State University, and before that, for about 60 years, I was an engineer and project engineer for different companies in Washington, D.C. area.
Mm-hmm. And can you please talk about the research center you run? I think it's quite big and comprehensive regarding control and robotics. Can you please tell us about the focus and research areas of it?
Sure. The center called Center for Intelligent Systems Research focuses on intelligence systems, information processing, and mathematical modeling for solving various problems in highway automation and what's known as intelligent transportation systems, as well as some applications in robotics, especially when they're relevant to the vehicle industry, like mobile robots, etc. This is a complementary center to another center that I helped establish and was the director for 5 years in the past, called National Crash Analysis Center at the George Washington University, which focused on other aspects of safety of vehicles, which was crash worthiness of the vehicle and structural and occupant protection design and analysis of the vehicles. So this center, which is CISR, Center for Intelligent Systems Research, focuses on areas to avoid crashes altogether, or to help drivers to drive either safer and safer as well as more efficiently. Areas that some of which we have seen in the car automotive industry in recent years have been subject of research about 15 years ago.
Thank you. I think, as you know, to prepare this interview, I've been snorkeling in that impressive book you recently edited, the Intelligent Vehicles Handbook. As a matter of fact, I have to say it's a very comprehensive and interesting document. Congratulations, and thanks for putting all your efforts into that useful piece of literature.
Yes, that the Handbook of Intelligent Vehicles has been the result of work of many people. It's obviously a comprehensive book about the subject. There are about 12 other associate editors that helped me put that together, and I'm very thankful to all of them, and thankful to many authors. So over 90 authors contributed to various chapters and sections of that handbook. The motivation for that handbook has been we were looking for a resource that could be available to engineers and researchers and students, or even people in industry that are looking for the latest technologies and methods that deal with vehicle automation, deal with vehicle safety, driver assistance systems, and things of that nature that comprise part of what we know as intelligent vehicles. And a comprehensive source of this nature did not exist in 2011, 2012. The project actually took about 2 years. We started earlier in 2010 and started writing different sections and chapters of that handbook. So it kind of fulfilled a gap in the technical literatures that dealt with intelligent vehicles. So hopefully it became a successful project according to the publisher, and has been very well received. Excuse me, has been very well received in the research community. It is a reference handbook, so mostly libraries and universities are interested and they order it. And the beauty of it is that the publisher has also made it available online electronically. Mm-hmm. And in addition, the availability is not just the entire 2 large volumes, but it is available at section by section or chapter by chapter. So a lot of researchers just go to that area that interests them and download that section. And from what I heard from publishers, it has been very well received, and it's as of last year, the number of downloads of this handbook has been perhaps twice as much of downloads of chapters of other similar handbooks. So that was very reassuring that the work that have gone into it has been well received by the research community. Yeah, and again, it really focuses on several different aspects of intelligent vehicles. So whatever that comprises what's known as intelligent vehicles is pretty much either covered in depth in various sections of this handbook, or there are excellent references that are provided by each chapter that the reader can go for further understanding and more focused study on the subject area.
It's good stuff, I can say. Well, I think in that book you author a chapter titled Fundamentals of Driver Assistance. Can you please share with our listeners, according to the state of art, what is driving assistance in these days?
Yes, certainly. Driver assistance has several aspects, and as the name implies, it's a system or technology that is in a vehicle that helps the driver to drive better or safer. Now, it could have various levels of interaction with the vehicle, between the vehicle and the driver. So various levels of interactions with the driver. For example, there are some driver assistance technologies that are already embedded in the design of the vehicle and pretty much work automatically, and their function is totally transparent to the driver. And this has been around. Those kind of driver assistance have been around, and some call it just active safety, but not driver assistance. But in the big picture of driver assistance, I think that is a subset of the systems that are available. And those are things like electronic stability control or ABS that are available. And then when you're functioning the vehicle, you're driving the vehicle, they automatically kick in when needed. So they are part of the automatic design of the vehicle as part of a safety or maneuvering of the vehicle. Now, there are other levels that deal with more interaction with the driver. And even that could be categorized at different levels. For example, you can provide information to the driver. Navigation systems are very popular in many vehicles right now, and they provide support to the driver to find out how to get from point A to point B. And yet, in another level of interactions, there's driver assistance technologies now that more in line with active safety, and they alert the driver or warn the driver of a potential hazardous situation. Therefore, the driver could avoid that situation and avoid a possible crash. For example, blind spot detection will help the driver to know the surrounding of the vehicle and not to change a lane when it's unsafe, whereas by looking in the mirrors, necessarily the driver could not find out that potential danger. There are yet other things. There are many of those now in some of the vehicles, either as standard options and others as additional options that you can purchase. For example, lane departure warning, which looks at the road ahead and figures out when the car is actually unintentionally is departing the lane and crossing the lane boundaries, and provides an alert or a warning to the driver, both audio and visually in the instrument panel. Some go beyond that and then provide the warning at the head-up display, which would be probably more effective warning to the driver. So these are all driver assistance technologies that are appearing in the automobile industry today. And the reason for them is because the computing power has become less expensive and much more powerful. Sensors have become more powerful and less expensive. Cameras are available in the vehicle. Radars are available in many vehicles to detect obstacles, for example. Other systems like infrared technology could augment the driver's vision at night. Night vision enhancement, for example, could show a potential animal or deer crossing on the road, whereas with naked eye, the driver would not see that. So, and then consequently, when the detection is performed by the sensor, there is some sort of signal to the driver that, be aware that there is a potential danger ahead. So these are the kind of things that the driver assistance systems offer to drivers, and they are emerging more and more. One of the things that I think is, we are seeing in the automotive industry is brake assist system, whereas there are different versions of this system as well, where you have braking capability of the vehicle that could, a novice driver or drivers that may be afraid in a hazardous situation cannot perform to the fullest capacity of the brake. Imagine an emergency scenario and the driver sees it, presses on the brake pedal, but doesn't press hard enough. Therefore, the brake will not, be executed and minimize the distance or maximize the stopping distance. So, therefore, the brake assist system can sense whether the driver is facing an emergency by sensing the force on the pedal or the rate of the application of the foot force on the brake pedal, and apply brake to the fullest capacity, because after it sensed that it was an emergency and the driver intention was to do a full brake but could not do it, the vehicle would support the driver in that function and stop the car as best as possible. So these are all different levels, different examples of driver assistance that are emerging in the vehicles. However, to get them into the vehicles, there's a lot of underlying research and development that goes on before they become available. You have to know how to interact with the driver. You have to know when best to apply these systems. They have to have reliable sensors that can detect the situation. So in case of warning or alerts, there are not false alarms or nuisance signals sent to the driver. In case of application or actuation of the vehicle, the function is performed properly, so it does not conflict with other functions of the vehicle. So there's a lot of both mechanical, electrical, and control system development that goes into, as well as human factors testing that goes into designing these systems before they appear in real cars.
Mm-hmm. That's interesting. Well, that chapter starts with I think with a good definition of driving. I will quote, with your permission. It goes like this: driving is a complex task of strategic decision-making, maneuvering, and controlling the vehicle while responding to external stimuli, traffic laws, and imminent hazards. Azim, drivers are human, what means that the center of driving relies on a quite unpredictable, clumsy, failure-prone controller, and also a quite different controller every time. So how do you think driver assistance cope with that unpredictability and variability?
Yeah, I mean, you pinpointed a very good and important question about the driver's role in driving, which is at the center of the driving, and why all of these driver assistance technologies are emerging right now. The challenge is how to best help the driver in active safety systems or alert systems, how to best support the driver when needed. Now, there are different strategies that have been exercised in real life in production cars, and most of them, and almost all of them, have the strategy that you make a system that is generic in nature, and the drivers will adapt to that system. For example, you provide an alert at certain points, and drivers will know and adapt that this alert will come on if they face that kind of situation. That is one approach that has been exercised most of the time. Or you create a steering feel that is standardized for that particular class of vehicle, and people will adjust to that steering feel, or the feel for the gas pedal or brake pedal, etc. But more and more researchers are looking into alternative approaches of doing that. That means that they're looking at how to best provide adaptive systems which are more adaptable to the driver's capabilities. Now, different, as you very well mentioned, the different drivers have different skills, they have different control abilities, they have different perception, reaction times, etc. So when you're dealing with emergency scenarios, you have to be very careful how to design an active system that actually interacts with the driver, or how to provide partial control of the vehicle when the driver is still in control of the vehicle. This is a very, very challenging part of the driver assistance, and perhaps the most difficult and challenging part, because there are elements of systems that need to be worked on. One is the sensing of the situation, which replaces the driver's vision or perception of the situation ahead. So the variety of sensors that are available today provide a condition or situational awareness that kind of matches or complements what the driver senses ahead. Then there is decision making on that sensor data. Prior to that, obviously, this multiple sensor data have to be fused together to make a coherent situational awareness, and there has to be a CPU or a brain of the system that understands, captures all that fused sensor data, and then makes sense of it, reasons with the situation ahead, and then makes a decision, and that decision is executed in terms of some sort of actuation. Now, that actuation could again could be a different level of warning or alert to the driver, or it could be supporting the driver function, or in more futuristic models that are referred to as driverless cars or autonomous cars, take over the control of the car. So these 3 or 4 functions of sensing, situational awareness, reasoning, making a decision, and actuation are the elements that will be work together to support the driver. Now, as you said, that the drivers are different. So how we support the drivers will probably needs to have certain level of adaptability. Now, adaptability comes into picture when you're dealing with situation that may not be totally emergency situation, because in real true emergency situation, when there is an imminent hazard, then you want to stop the vehicle as safe as possible or redirect the vehicle as best as possible without creating other potential dangers. In those scenarios, then maybe in the future a takeover control of the vehicle may be the best option. In situations when there is less of emergency, but more of a comfort of driving, for example, if somebody is going too fast on entering a curve, a reduction of speed may be necessary. A warning could be executed. Currently, you can have an alert that if your speed is too high or you're entering a curve at a dangerous speed, and expect the driver to do the reduction in speed. An alternate approach could be that you make speeding more difficult for the driver. For example, the gas pedal would be stiffer, so speeding will be prevented, basically. So that is an alternative adaptive system that may work best as an active safety system. Now, another aspect of that deals with the variability of the driver. That is, you create a support system that is adaptable to the profile of the driver itself. So, I'm sorry, which is adaptable to the profile of the driver himself or herself. That means that you know how the driver performs in this situation by collecting data and then having an intelligent model that corresponds to that driving behavior, and then providing alerts or support systems that can best help that particular profile. So that's a different level of support that considers the variability in the drivers.
Thank you. Well, I think I've seen that feature you shared in your book about the relationship between driver, vehicle, and environment. And in that feature, it seems that communication between these three plays a major role in all about driver assistance. So connected vehicles again? Do we need to turn our cars into connected appliance to drive safer?
Well, yeah, that's basically what that figure is referring to, is emphasizing that there are three elements in the driving environment that are really inseparable elements if you're considering safety or considering improving the either the safety or the efficiency of the driving. That is the driver, the vehicle, and the environment, because the driver has a major role in controlling the vehicle, and the vehicle has certain functionality and certain performance level, which is affected by the environment. A vehicle that steers one way on a dry surface may be different. It is different on an icy surface. Now, if you want to have a system and there is a bridge that is probably icy in the winter time and it's on a curve, then a driver entering that bridge or that curve that is icy condition, then if the driver is to be warned, there has to be some information from the environment to the vehicle and from the vehicle to the driver. So this is an example of one simple system that all three elements need to be connected to each other in order to provide the driver assistance systems. So it's the significance of that diagram is really the communication, then the link between these three elements. Now, it is not far-fetched to imagine that there is data available from the infrastructure on the highways or roadways, and that information from weather or road conditions are transferred to the vehicle and from the vehicle to the driver. So that's the significance of that figure. And the next generation of the vehicles where autonomous driving is becoming possible, or more driver assistance systems and higher level of automations are becoming possible, then the concept of connected vehicle, where the vehicles are actually communicating with each other to perform better and to provide better throughput, less traffic, and safer driving is becoming possible through various studies that are being conducted, the research that is being conducted on connected vehicles. The terminology connected vehicles is really referring to vehicles that through wireless communication can communicate their information to each other or to an infrastructure nearby, or sometimes even to an infrastructure central system or traffic management centers. Now, there are various applications of the connected vehicles that one can imagine that could be possible through communications that enhances the safety. One is the intersection, which is one of the major safety areas, potential for collisions at intersections where their visibilities are limited or where there is intruding traffic that are not obeying the traffic signals or missing the traffic signals altogether. So you can imagine an intelligent intersection that has communication with two different directions that are not visible to each other, but if there is an intruding vehicle potentially crossing intersection that has a red light, but the driver, for whatever reason, is not seeing the red light or is not obeying the red light, then it could be warned, that driver could be warned that you are about to do this, or the drivers that are potentially in a hazardous situation coming from the other direction into the intersection could be warned of this hazardous situation, and even though their light is green, they could slow down, or the vehicle could alert the driver, or maybe, again, in the future, control the vehicle so the vehicle will not enter into a hazardous collision situation. So there are several different applications of connected vehicles that deal with safety or even efficiency. One can imagine another scenario where you going around a curve at a highway speed and you don't have visibility, but around the curve there is a stoppage for whatever reason, and then if you continue with that speed, you will be hitting the vehicles or rear-ending the vehicles ahead. We have seen rear-ending of multiple vehicles in highways on several different occasions. So connected vehicles could have this information and pass the information, safety information, to the vehicles that entering that situation, and the vehicles will slow down either by the driver's control or automatically. So these are just a couple of simple examples of connected vehicle safety applications, but there are many other applications that vehicles talking to infrastructure or vehicles talking to each other could be performing better together. For example, platooning of trucks, or platooning of the multiple vehicles, which refers to vehicles that are following each other in a constant distance or constant time with each other, relative to each other, and they're all moving with that distance or time relative to each other in a constant speed. By doing so, they're improving the traffic, they're improving the efficiency, and in case of trucks or even some vehicles, they're improving the aerodynamic resistance. Therefore, the efficiency of the vehicles will be better. And if this is in coordination with other traffic, they can improve the traffic on different roadways. So there are several different scenarios of connected vehicles that are being studied extensively, and all of them for improving the driving safety and driving efficiency.
Mm-hmm. You have another chapter about what you call intelligent speed adaptation, so I think it's quite related to these examples you have been sharing. Is that so?
Yeah, I mean, that was a project that we work on. Primarily, our perspective was the safety by controlling the speed. And intelligent speed adaptation, or ISA, refers to systems that somehow warn the driver of their speeding. Now, whether the drivers are speeding above the speed limit or whether they're driving above their own normative behavior is of a concern and issue here. And the fact is that you can have systems, and some of them are currently available in vehicles, that warn the drivers that they are speeding beyond the set limit. Now, there are different levels of this as well in terms of warning or alerting the driver, and they have been tested by different research groups, including ourselves. Our testing was done in a driving simulator, and the purpose was to understand the effectiveness of speed control. Speed control has several aspects, obviously. The one aspect is the safety aspect, that you control the speed to you minimize the potential for collisions. Other aspects are speed harmonization, which if you do it by either voluntarily or by, again, in the further future, by control of multiple vehicles, that speed harmonization may provide efficiency in driving. Now, how you in terms of safety, what we examined for intelligent speed adaptation was examine different alternatives for ISAs. One alternative that you can maintain a safe speed is obviously a speed limiter. Speed limiter is a device that you can add to the vehicle that does not allow the vehicle to go above certain speed limit. And most of the studies, almost all of the studies that we have reviewed in the literature, and including our own human factor studies of such systems, showed that their acceptability is very low. In general, put it in a simple terms, people do not like speed limiters because they feel when they need to speed to go, to pass a vehicle or a certain situation, merging in highways, etc. They do need to have full control on the speed of the vehicle, and they do not like it when that control is taken away from them. So
part of the fun.
So speed limiters are not, is known that it's not acceptable. So alternatives are providing information only to the driver or continuous alert to the driver if they are exceeding speed limits. So we have evaluated these different alternatives on different roadways at different speeds, even with conditions that we profiled drivers. That means we actually profiled in individuals' normative speeding behavior. That is usually a few miles, for many people, a few miles over the speed limit. So we created a warning system in the instrument panel where when they went over the speed limit of the assigned speed limit of the roadway, they got a yellow warning and a signal. And then when they went over their own normative speeding behavior, they got a red signal as well as a different audio signal warning them of a more hazardous situation. And then tested them versus no system in place and versus a total speed limiter for different segments of the highway, and as I said, for different speeds. And we came up with a lot of different statistical measures of how people perform under those situations, whether those warning that we provided were effective or not. And for certain segments of the highway, mostly on the freeways and the where the higher speeds, they have shown some effectiveness. The system that was adaptive to the driver's own profile was more acceptable. Of course, to that, we added another safety feature that in addition to the warning, we made the gas pedal a little stiffer, not totally limiting the speed, but making it stiffer to speed beyond their own normative behavior. And that system, together with the adaptive warning, visual and audio warning, proved effective in certain highway scenarios. So speed control is possible to a certain level if you have an adaptive active safety system, in my opinion. Its acceptability differs from person to person, and it is from community to community. But I think knowing that the speeding has been or continues to be one of the major contributors to severe crashes, I think that's a system worth considering for the future.
Mm-hmm. Well, now we need to make a very short break, but we will be back in a few seconds, so please wait for us. Hi again, we are recruiting volunteers for the ITS podcast. If you like our show and you think you can share some of your time with us, please let us know. Send us an email to ITSPodcast@gmail.com. ITSPodcast@gmail.com. We will appreciate it. Now let's get back to our today's interview. Thank you. We're back with Professor Eskandarian talking about active traffic safety. I think your center devotes a good deal of research to fatigue detection systems. It looks like a challenging task to do, especially beyond the detection. I mean, what happens is that if a system has a positive fatigue detection in a driver, what should we do then to prevent them from driving in the middle of the highway, or even worse, how preventing fatigue drivers to switch off that system if it becomes too annoying to them?
Let me go by the background of the fatigue and drowsy driving.
Mm-hmm.
But the drowsy driving, National Highway Traffic Safety Administration of the U.S. Department of Transportation estimates that about 16% of crashes were attributed to drowsy and fatigue driving. Now, it is hard. Drowsiness and fatigue is a hard thing to measure, obviously. Again, as it varies from person to person, and the control abilities of the drivers are vary from person to person when they're under fatigue conditions. A major issue with the statistic that I just quoted is that many people do not accept that they were drowsy or fatigued when they were driving. So understanding whether a crash that occurred was attributed to that condition or not is questionable by itself. So usually people in the research community that deal with this problem think that the problem is bigger than what the data shows, because especially for the drowsiness, because when people are drowsy, they really don't know what happens. And because of legal issues, some because of insurance concerns, do not admit that they were actually drowsy. So the problem may be bigger than the data reflects. Now, the challenge in that is twofold. One is how to detect the condition of the driver, fatigued or drowsy. And the second thing is what to do with that information if you detect it correctly. So if you detect somebody is drowsy or fatigued, you provide a warning to them, obviously. And that's your question: what should be the nature of that warning? What do we expect the people do when they receive that warning? First, let's focus on the detection part, because that's a very important aspect of it. If your detection system is not very reliable, then you tend to produce nuisance signals to the driver, and they will be annoying signals, and eventually a system of that nature will not be acceptable or will not be in place. If you do not detect well conditions where the person was actually fatigued or drowsy, then you're missing the detection, and you're creating a dangerous situation where the person actually is relying on your system. So detection in that scenario is, in my opinion, is the more difficult challenge. And there have been different methods of detection that have been tested in laboratory setting as well as in real life. A lot of the detections focused on eye monitoring and facial monitoring, which correspond very well to the state of the driver. And unfortunately, although in research and lab environment they may have worked to a certain degree of success, in real life some of these systems were not that effective because of the eye monitoring systems that did not work properly, because of the reflection, because of the lighting, because of the situations where the driver may be wearing glasses, or the head of the driver is moving a lot and the detection is not robust enough to handle those situations. So there were problems with that mode of detection. Alternative detections are physiological detection of heart rate, perspiration, EEG signals, brain signals of the driver, and other physiological measures that are reflective of a person's fatigue or drowsiness condition. And they have been tested with certain success as well. Yet another alternative for detection is look at the performance of the driving. By performance, I mean the handling of the vehicle by the driver, and comparison of the handling of the vehicle in fatigue situation or drowsy situation versus the normative driving situation. And our research, as well as many other researchers, have shown that people's steering is particularly affected by fatigue condition. Basically, what happens in most of our driving is we are trying to keep at the center of the lane. And what happens when we are fatigued, our perception will have a slight delay. Therefore, it will take a little longer when we are off the center of a lane. And then our reaction will be slower to that condition, so it takes a little longer to bring the vehicle to the center as we go off the center. So if you look at the steering signal of a fatigue driver, it is a signal that has a different amplitude, probably higher peaks and valleys in that signal, and totally different frequency of correction versus the normative behavior of the driver, where the signal is more steady with smaller amplitudes. Now, due to variability of the person to person, the perception response is different, therefore this steering function is also different. Some people's normative behavior has a lot more corrections than others. So the problem becomes very complicated in that sense as well. In our research group, we have came up with a signal processing method that could capture that difference effectively, at least with about 86% of success rate in detection in limited subject studies that we did in a driving simulator. Based on the steering performance of the driver, we were able to distinguish their state of drowsiness versus non-drowsy driving. So that's from the from the detection side. Now, what to do after you detect that a person is in a fatigue condition? Obviously, there's alternative methods of warning or alerting the driver of this thing. Now, if the person is in a total drowsy state, because drowsiness or fatigue is not a 0 or 1 or yes or no condition. It's really a continuous and changing condition. So people slowly get into it, and then they may come back to their normative state and then go back to that drowsy or fatigued state again. So it's a very difficult and challenging problem. So when to warn is challenging. After the detection is done, there are different ways you can warn the driver, either by audio signals, like you can call it a wake-up call of some sort, or you can have other haptic feedback that have been tested before. For example, the vibration on the seat, the vibration on the steering wheel, or a combination of light and sound and vibration to kind of bring the attention to the attention of the driver of his or her state that could be potentially a dangerous state. So, but that has to be very carefully done to make sure that you're not creating a more hazardous situation by an abrupt signal to a fatigued driver. That part of that is alleviated if your detection mechanism is very strong and very robust and reliable, and you can detect early enough, not after the driver has crossed the lane or is going off the road, but early enough based on their either facial or eye monitoring, as I mentioned before, or other techniques that we have devised in terms of their steering monitoring or driving, monitoring their driving characteristics. So if that part of detection is robust enough and you can do it early enough, then the job of the warning or alert of the driver becomes a little simpler or easier and safer. Now, there are other alternatives that can be tried. For example, if somebody is a truck driver doing carrying hazardous material, maybe a warning to a dispatcher could be helpful through communication, and the dispatcher could engage the driver and speak with the driver to make sure the driver knows of his state or her state and slows down the vehicle or parks the vehicle. That's where it's not an emergency condition. In terms of emergency condition, alerting the driver by haptic signals seems to be a very effective method. And then eventually, if there's a very hazardous situation where it's life-threatening, maybe executing the brake with a brake assist system will also be a good addition to bring the vehicle to a safe stop at some point. Mm-hmm. Now, I say this in light of research that has been done for rumble strips. Rumble strips are these grooves that are on the side of the highway when you go off the roadway, and it creates a vibration and a sound. And they have proven by several studies that they are very effective in waking up the drivers or warning the drivers when they have crossed the roads and they need to bring their vehicle into the lane or stop the vehicle. So many studies have shown that rumble strips are very effective systems in alerting the drivers. So you can imagine the function of a haptic vibration on the seats or on the steering wheel together with the sound that resembles the effect of the rumble strip will be an effective system, similarly effective system for fatigue or drowsy drivers.
Mm-hmm. Well, we are reaching the end of this interview. I think I've read somewhere that when we have fully automated driving, we will not even notice the change. I mean that the change will be so smooth, we will not have to face any steep adaptation curve. So what do you think? Where do you put your chips? You think we will release the steering wheel for the sake of safety? Or will we always reserve from the computer some of the fun of driving for the humans?
Well, this is a very good question that is emerging more as we've seen more in media and in the research community and the automotive industry, the emergence of the so-called driverless or autonomous cars. It really depends what driving mode will be emerging in the future. I think that the driverless cars or autonomous cars have their place, and I think they certainly will emerge. There are certain situations that lend themselves very well to autonomous vehicles, and there are other situations where the support for drivers, or what we've been discussing today in terms of active safety systems or advanced driver assistance systems, are very applicable. I see a future of the auto industry where there will be more and more of these active systems and advanced driver assistance systems in place, where they not only provide warning and alert to the drivers, but they also take partial control of the driving where safety is concerned. And they enhance the performance of the driver for the sake of safety, to minimize crashes, to minimize injuries to the drivers and occupants. So there is a line between supporting the driver, taking over partial control, and then taking over total control of the vehicle. It really depends on what hazardous situation you're considering or you're faced with, and different segments of these systems could kick in and be triggered and support the driver in that sense. So all the examples that we talked today showed driver assistance at different levels. You can imagine that once you have autonomous capabilities, then you can switch from the regular driving to autonomous driving. Now, again, there are totally different conditions when we're talking about normative driving or we're talking about emergency scenarios. Hopefully, the systems that you will see in the future will all be very seamless to the driver. The only way that they will be successful if they are just as seamless as electronic stability control and all these other systems that are currently available that support the driving without the driver even noticing it. So if we are imagining autonomous driving by choice, then you can imagine a driver sitting in a car, putting a destination, and the vehicle will take the car to the destination. If you're talking about autonomous driving in terms of a support to the driver, then there's more focus in that in the driver assistance systems, and the driver assistance systems will kick in terms of a support to the driver as much as possible, and then in the future, hopefully, we will know more about the driving behavior, and we will have more adaptive systems that are adaptable to the individual driving behavior. And the active safety system will kick in when they are best needed to avoid hazardous situations or just support the normative driving of the individual drivers.
Mm-hmm. Okay, thank you. Well, this is the end. Azim, thank you so much for your very pedagogical, insightful contribution to this publication. Please keep doing what you do to keep us all alive while driving, while we still drive. So, thank you.
Thank you very much. And thank you for the opportunity to discuss these important issues.
Okay, goodbye, Professor.
All right, goodbye.
Well, we're reaching the end of this episode. How was it? Did you like it? Do you want to comment it? We really love your feedback. We are all ears for our very special listeners and followers. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, language advisory by Manuel Arbelo and Professor Son Williams from Clemson University, South Carolina. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Have a happy holidays and please drive safe.